Welcome to Unit 3. In Units 1 and 2, we learned about symmetric ciphers and how to use them. Symmetric ciphers assume that both parties have the same key. The important property that makes them symmetric is that the same key is used for encrypting and decrypting. In some scenarios, this is okay. When we talked about using symmetric ciphers to encrypt a file, well, we could assume that the same party is encrypting and decrypting the file so they can create and keep the key locally. But when we talk about using symmetric ciphers for most applications that involve more than one party, this is a big problem. If Alice and Bob want to talk together, well, they have to first agree on this secret key. There has to be a way for Alice and Bob to communicate that key without exposing it. They can't send it over the insecure channel. If they could send a secret key over an insecure channel, well, they wouldn't need encryption at all. In the early days, this was done having a secret codebook that was physically distributed to the endpoints that were communicating. With Colossus, this was the codebook that had the keys for each day, and that was physically distributed to the capitals where the Lorenz machines were. With Enigma, this was physically distributed to all the ships, and captains were under very strict orders to destroy those codebooks anytime their ship was in danger of being captured. This was the most important thing to destroy on the ship, to make sure the enemy didn't capture the codebook. For most applications, especially any civilian application in the day of the internet, distributing a physical codebook or having two parties meet in a secure place to exchange a key is not very practical. What we want is some way to establish a secure key or some way to enable two parties to communicate that doesn't require that. So that's the main topic of this unit. We're going to look at different ways that we could enable this kind of communication without starting from advance where Alice and Bob have a shared key. So the first approach I'll talk about, I'll call solution number 0 because it's really not even approaching a solution, is to have pairwise shared keys. And the idea here is for everyone who ever might want to communicate to get together, form keys between them. So let's say this is Alice, Bob, Colleen, Diana, someone whose name starts with E, and someone whose name starts with F. And Alice would set up a pairwise shared key, secretly communicating with each of the other people. Bob has a shared key with Alice. Bob would find a shared key with all the other people that he might want to communicate with. And Colleen needs to find a shared key with the remaining people, and so forth. And you would have a key between every pair of people. And so whoever wants to communicate, well, if it's between Colleen and Edgar, they would have a shared key that they've previously established to communicate. So this might work for a small number of people. If we have a large number of people, this gets to be ridiculously expensive. So we'll have a short warm-up quiz to see how expensive. So the question is, how many keys would we need if there was a group of 100 people and any pair of them should be able to communicate secretly with each other? So the answer is 4,950. The way to think about that is if we have a group of people, and I won't try to draw 100 people, but let's say we have 4. Alice needs a pairwise key with Bob. She needs a pairwise key with Charlie, and she needs a pairwise key with Daniel. That's 3 keys for Alice, and so that's the number of people minus 1, since she doesn't need a key with herself. Bob already has a pairwise key with Alice. He needs one with Colleen, or maybe that was Charlie, and he needs one with Doug. So Bob needs 2 pairwise keys, which is n minus 1 minus 1, since he already has one with Alice, and he doesn't need one with himself. And that keeps going until we get to the last person, who already has keys shared with everyone and won't need a new key. So we could compute that in Python, and this would compute the sum of the numbers from 0 to 99, which is 4,950. We could also compute this using the formula. We have n minus 1 plus 1, that's n, times n minus 1 over 2 occurrences of that. So that would be equal to 100 times 99 divided by 2, which is the same answer we got by summing all the numbers using Python. So this means the number of keys that we need scales as the square of the number of people. So if we think about doing this for a group of people as large as the internet, where we say have 10 to the 9 or a billion people, we would need 10 to the 18 keys to have pairwise keys between each pair. This is a ridiculously large number of keys. So I'm going to discuss one other non-solution. So we'll call this one number 0b, which is to use a trusted third party. So here's the idea that we have some very, very trustworthy place, and we'll make it green. People trust things that are green. So we have this very trusty place called Trusty Keys. And Trusty Keys has a shared secret with each individual in the network. So now if Alice and Bob want to communicate, The protocol is Alice sends a message to trustee keys that says she wants to communicate with Bob. So that's step one of the protocol. What trustee keys will do is generate some new key, some new secret key, and we'll call that KAB because it's for Alice to communicate with Bob. So in step 3, trustee keys will send the new key to both Alice and Bob, and it will send it encrypted using the key that's already shared between those two parties. So what it sends to Bob is the encryption using KB, the shared key between Bob and trustee keys, of something that says Alice's name concatenated with the actual key. And what gets sent to Alice is encrypted with KA, the shared key between Alice and trustee keys, and the name Bob along with KAB. At this point, both Alice and Bob know KAB and can communicate securely using KAB to encrypt messages between them. So the quiz, to see if you understand third-party key distribution, what could go wrong with this protocol? So the choices are trustee keys can read all the messages that happen between A and B over their encrypted channel. Trustee keys can impersonate any customer that shares a key with trustee keys. And some evil party C could tamper with messages in step 3 to steal the key AB and set up a different key between Alice and Bob and then steal their traffic. So the answer is definitely the first two, maybe the third. So in the first case, trustee keys generated key AB. That's the key used to protect these messages. So any message over this channel that trustee keys can intercept, it can read. Trustee keys can impersonate any customer because it has a key shared with them, can generate a fake channel, make it seem like Alice is talking to Colleen, but pretend to be Colleen in that communication. And finally, if there's a malicious party C, well, maybe they could tamper with messages along these channels. I didn't provide enough details on what we're using for encryption here and what mode of operation is used and other details to know whether or not that's possible. Let's assume we could solve this problem. These other two are really big problems, and there's no way to solve these if we're using a third party to generate our keys. We also haven't solved the key distribution problem because we still needed to set up all these shared secret keys between trustee keys and every other party. So we haven't really solved our problem. This would only work if everyone completely trusted trustee keys, which seems unlikely even with the green box, and if there was a secure way for everyone to establish a shared secret key with trustee keys. The next thing I'm going to talk about is an idea that Ralph Merkle came up with in 1974. It's not a practical idea at all, but it's a really clever idea, and I think it's a fun thing to talk about before we get into the more realistic solutions that are used today. So the idea behind Merkle's puzzles is that you have the two parties that want to share a key, and we'll call them Alice and Bob as usual. First, they have to agree on some parameters. They agree on an encryption function. They agree on security parameters S, N, and uppercase N. So the basic idea is Alice is going to create many puzzles, send them to Bob. Bob will randomly pick one of the puzzles to solve, and part of solving that puzzle will give Bob the number of the puzzle and a secret. And what he'll send back to Alice is the number of the puzzle, and Alice will know the corresponding secret, and they'll use that as the key. So let me go through this in a little more detail, but that's the high-level idea. And the reason that this gives you a way to establish a key is because Bob's randomly picking one puzzle to solve, whereas an attacker would have to solve many puzzles before they could get the one that Bob actually solved. So here's how the steps work in a little more detail. So in order to create puzzles, so Alice creates a list of n secrets. Each one of these is a random number, s bits long. Then she creates a set of messages, also n messages, and each message will be encrypted using the encryption function that they agreed on, using a key that's the corresponding secret concatenated with enough zeros to make the appropriate key length. So if this was a 128-bit AES key, the secret size might be, say, 40 bits, and then we would add zeros to fill out the rest of the key. And then what we'll encrypt using that key is a message that says, gives the identity of the puzzle, which will be that index. And the message will give the identity of the puzzle, and we'll include a string before it so it's clear that that's the right message. If we just included a number, if there were enough numbers, we might accidentally decrypt one to that. So that's what we encode for each message here. After this, Alice shuffles the messages, and then she sends all n messages to Bob. Bob randomly picks one of those, then does a brute force key search, where Bob is trying to decrypt using a guessed key concatenated with n minus s zeros, the message that Bob randomly selected from those puzzles. Eventually, he's going to find one of these decrypts to puzzle followed by a number. At this point, Bob knows the guess, so he knows the secret that was used for that, and he knows the puzzle number. If we wanted a larger key, which we probably do, what we should include in the puzzle, instead of just the I, we should include a key. And this means the key can be of any length. This would be some new random key associated with that puzzle. Alice would keep track of those keys. And so for each puzzle, when Bob decrypts it, he acquires both the puzzle number and the key number, sends the number of the puzzle back to Alice. Alice can look up in her keys, figure out which key was the one in the puzzle Bob decrypted. So assuming encryption and the random number generation work perfectly, the question is how much more work does an eavesdropper have to do than Bob has to do? And an eavesdropper hears all the messages between Alice and Bob, wants to determine the key that they'll use to communicate. So here are the choices. It's impossible for the attacker to find the key. The attacker would need to use n times as much work as Bob to determine the key. The attacker would expect to need n over 2 times as much work as Bob, or the attacker would be expected to need twice as much work as Bob. And the value of n is the number of puzzles that Alice creates and sends to Bob. The answer is that the attacker would expect to need n over 2 times as much. The reason for this is because of this step. Bob randomly picks one of the puzzles and solves just that puzzle. Once Bob has solved it, he sends back the number of the puzzle that he solved, which was part of the puzzle, to Alice, and that establishes the shared key. An attacker can hear that number, but doesn't know which of the encrypted messages corresponds to that. So the attacker would need to try and break all of the encrypted messages and would be expected to find the one that matches the one that Bob picked after trying about half of them. So this is a neat idea. That n over 2 advantage is really not enough. For that to be significant, we would have to have a really large number of puzzles. That involves a lot of work for Alice. Alice still needs to create all those puzzles and requires a lot of bandwidth. We'd have to send all those puzzles across the network. So a very impractical idea. So the first real solution to this problem, and one that is frequently still used today, is called Diffie-Hellman key exchange. It was first published by Whitfield Diffie and Martin Hellman in a very famous 1976 paper. It was actually discovered a few years earlier than that by Malcolm Williamson, who was working at the British Government Communication Headquarters. This is the successor to Bletchley Park. It was kept classified, so Williamson didn't get credit for this, and it wasn't known that it had been discovered earlier there until quite recently. And this idea came from a paper that Diffie and Hellman published in 1976. I mentioned Shannon's paper as one of the 3 most important papers in cryptography. This is one of the other 3. The third one, and I'm not trying to put these 3 in order, just chronologically, is the RSA paper that we'll talk about a little later. But this paper really introduced the idea of public key cryptography. It didn't provide a solution. It provided a solution to part of the problem. So they started with this introduction about we're on the brink of a revolution in cryptography, and posed the question of, can we build cryptographic tools that are the equivalent to a written signature? There are lots of other kinds of applications they talk about in the paper, as well as the idea of basing crypto systems on known hard problems or believed to be hard problems. The one solution that is in the paper that we're going to talk about today is this Diffie-Hellman key exchange protocol. And it's actually quite a simple protocol. It's still very widely used, and it allows 2 parties, without any prior agreement, to be able to establish a shared secret key. So before describing it mathematically, I'm going to describe it as an analogy to paint mixing. And this analogy comes from Simon Singh from the Codebook, which is a really fun book about the history of cryptography. So we have our usual suspects, Alice and Bob, that want to establish a shared key. And they're going to do this by first picking a public color. Let's say they both like yellow, and they'll start with cans of identical yellow paint. So both Alice and Bob start with a can of yellow paint. Then each party will pick their own secret color. So let's say Alice picks a greenish color, and Bob picks a purplish color. Then what they do is mix their secret colors with the public color. So they're going to mix those 2, and the green and yellow will make some ugly green color. And Bob will do the same thing, mixing the yellow and purple to get some new ugly color. So at this stage, they exchange colors. Alice gives Bob the ugly green color that she got by mixing her secret color with yellow. Bob gives Alice the ugly pinkish color he got by mixing yellow with his secret color. Once they've received the other party's colors, they mix their secret color with the other party's mixed color. At this stage, both parties should have the same color. So Alice mixed her green with the pink that came from yellow and Bob's secret color. And that'll give some new color, probably uglier than the gray that I'm drawing. But Bob will get the same thing because Bob is mixing the yellow, Alice's secret color, and Bob's secret color and getting the same color out. So this gets them the same color. They've mixed the same three colors together. It would be secure if someone who knew yellow and could intercept these two transmissions couldn't guess the secret colors. This assumes that paint unmixing is impossible. Probably not a very good assumption, and certainly not a practical way to actually do this. What we want is to do the same thing with mathematics. This is also the main operation we used in symmetric ciphers. XOR is plus modulo 2. To do key agreement, though, plus is not going to be the main operation. The main operation we'll use is multiplication. To do this with math, the main operation we need is multiplication. There's a few key properties of multiplication that we'll take advantage of. The first is that it's commutative. That means that a times b is always equal to b times a. This is true on the integers. It's also true using any modulus. This property also holds for powers of powers. That means for any integers, a to the b raised to the c power. Well, that's equivalent to a to the b times a to the b times a to the b c times, which is equivalent to a to the b times c. We're just adding powers when we multiply here, which is also equivalent to a to the c times b. We know that from the cumulative property of multiplication, which is also equivalent to a to the c to the b. Using the same property here, a to the c, b times. These things are all equivalent, and they're also equivalent with modular multiplication as well. So that's the main property that Diffie-Hellman key exchange takes advantage of. And I'm going to show you the protocol next, and then we'll talk about why it's secure and some of the details in actually implementing it. So here's the idea of the protocol. First, they agree on two shared values. The first is q, some large prime number, and the second is g, and g is a primitive root of q. What it means to be a primitive root is that for all numbers in the group zq, that is the numbers 1, 2 through q minus 1, we can generate all those numbers by raising g to some integer power. If q is prime, it must have a primitive root, and there are ways to find these primitive roots. We could think of a brute force way of trying numbers until we find one. That would be very expensive for a large prime number, but there are more efficient ways to find them, which we won't talk about. So that's what they start with, those two things. And then here's how the protocol works. Alice will select a large random number, and Bob will also select his own large random number. This is like selecting the secret paint colors. Then Alice will compute a value we'll call ya, and she'll compute that by raising g to the xa power and doing this modulo q. Bob will do the same thing, but with his secret power xb, so he'll raise g to the xb power modulo q. They'll exchange these values. So Alice sends ya to Bob, Bob sends yb to Alice, and then Alice will compute a key that will be shared between Alice and Bob. And she'll compute that by raising the yb value that she received from Bob to the xa power, and do that all modulo q. If this is a good key distribution protocol, well then there should be a way for Bob to compute the same key. I'll see if you can figure that out yourself by making that a quiz. So these are the possible choices. Which one of these should Bob compute to obtain the same key as Alice did here? The answer is the first one. Bob should compute ya to the xb power modulo q. The second one would compute the same thing. This is in fact exactly what Alice computed, but Bob can't do this because he doesn't know xa. The third one wouldn't compute the same key. So the correctness property is that Alice and Bob obtain the same key. And we can show this by just plugging in the values. So the key Alice computed was yb to the xa. The value of yb is g to the xb. So that's equivalent to g to the xb xa mod q. The key that Bob would compute, and we'll write that as key ba since we haven't yet shown that they're equivalent using this equation. Well, ya is g to the xa, so this is g to the xa xb mod q. And we already showed that powers of powers are commutative, so these two are equivalent. So the next important property is that it's actually secure. And we're going to focus first on secure against a passive eavesdropper. So this is an adversary that can listen in on all the messages, but can't modify them. So that means the adversary will be able to get the public values, q and g. We'll also be able to hear all the messages transmitted. So we'll be able to learn ya and yb. And our goal is to be confident that the adversary would not be able to learn KAB. So the question is, which of these would be most convincing in proving that the Diffie-Hellman protocol is secure? The first is that showing that the number of possible XA values to guess is too high. The second is showing that an attacker who could solve a known hard problem would be able to compute the key. And the third is showing that an attacker who can compute the key would be able to solve some known hard problem. So the correct answer is the third choice. What we'd really like to be able to show is that we can reduce some known hard problem to the Diffie-Hellman problem. And the important thing is that this would show that anyone who can solve the Diffie-Hellman problem would also be able to solve some problem that we already know is hard. Showing that the problem is hard just shows that if we have a large enough instance of it, it can't be solved with a certain amount of computational resources. And we hope that by picking a large enough instance, we can make the work for the attacker far beyond what any attacker could afford. That does depend on this property. So it depends on the number of values being high. That itself is not a useful proof of security. What we need to know is that there's no easier way to solve the problem than trying all the possible values. The hard problem that is closely related to the Diffie-Hellman security property is the discrete log problem. Discrete logs are like continuous logs, but over a discrete group. So continuous log, if we have a to the x equals b, and we know a and b, we can solve for x. That's the log base a of b. And they're well-known, efficient ways to compute these logarithms. One of the earliest use of computers was to compute these tables of logarithms. With discrete numbers, this gets much more interesting. So now we have a to the x equal b modulo some value n. And our goal is to solve for x, which is the discrete log base a of b. And this turns out to be, as far as everyone can tell, a very hard problem when n is a large prime number. It's not clear that the discrete log always exists, and for certain choices of a, b, and n, it would not exist. But if we choose n as a large prime number and a as a generator, well then by definition, it must exist. What it means for a number to be a generator is that if we raise g to each power, what we get is a permutation of the numbers in the group Zn. So as a little demonstration, certainly not a proof, here's a code that produces the permutation for given some generator and some modulus, raises the generator to every power between 1 and the modulus minus 1. So we can try that with a fairly small prime number, so you can see the results. We'll use 277 as our prime number, and 5 as a generator for 277. One could check that in a brute force way, just show that it all produces all the numbers, and we'll see that in the output for generator permutation. These are the results. And you can see the first one is 5, that's 5 to the 1. 25 is 5 to the 2. 125 is 5 to the 3. The next one is 71, because 5 to the 4, mod 277 is 71. And if we look at all the numbers here, it would be a permutation on the numbers from 1 to 276. Other than the early ones, it would be fairly hard to predict where a number is in this sequence. You could certainly compute the whole sequence to find it. The question the discrete log is asking is, given a number, can you figure out where it would be in this sequence? Or can you figure out the power that you need to raise the generator to find it? And the claim is that that's hard to do. Showing the sequence certainly is not enough to convince you that that's hard to do. And there's no proof that it's hard. The reason people believe it's hard is that many smart people have tried to find good ways of doing this, and none of the solutions run in polynomial time, that the fastest known solutions are exponential. That means essentially that the only way to solve this is to try all possible powers until you find the one that works. You can do a little better than that by trying powers in a clever way, and you can exclude some of the powers more quickly, but you can't do any better than doing this exponential search, which is exponential in the size of n. So this is something we have to be careful about when we talk about hard problems. When we say it's exponential, well, it's not exponential in the value of n. It's linear in the value of n. We just need to try n operations. But the magnitude of n grows as 2 to the number of bits needed to write down n. So as long as that's the best solution to discrete log, then for very large n, it's intractable. No matter how many computing resources you have, you can't do this exponential search. You can't find the value of x that's the discrete log of b base a mod n. So as long as no one can find a fast way to solve the discrete log problem, as long as n is large and is an arbitrary instance of this problem, we think that it should be hard to compute x given a and b and the modulus. So for this quiz, we'll assume that we have an adversary that's passive. So all they can do is eavesdrop on the messages. But they also have access to a powerful computing resource. They have a procedure dlog that is a fast procedure for computing discrete logs that works on any inputs. And they have modular exponentiation, a fast procedure that outputs base to the power mod modulus. And now the question is, can they break a Diffie-Hellman key? So we're assuming that they're a passive attacker. So they've eavesdropped on all the messages between Alice and Bob. So they have all these values that were sent over the secure channel. And the possible answers are no, that it's impossible with no more resources or information, or that yes, there is a way to do it, and here's the way that she would compute that. The answer is the second choice. If it were possible to compute discrete logs quickly, and our adversary had a way to do that, well, then they could compute the discrete log of the intercepted value YA, the G and the Q values, which were also intercepted. Those ones were public. And the result of this would be the XA value that was Alice's secret. And then the adversary can compute the key the same way that Alice would. This was the only secret value. And if you had the discrete log function, you could compute that secret value. The second answer doesn't compute the right thing. It's computing the discrete log of YB, which would be the YA value. That's not the value that is necessary to compute the key. The third value doesn't use discrete log. If we could actually compute the key this way, well, then the protocol would be completely insecure because it turns out that modular exponentiation is a function that we can compute efficiently. And it's necessary that we can compute modular exponentiation efficiently because otherwise the legitimate participants in the protocol wouldn't be able to determine their keys. So we'll look at that soon. Before doing that, I want to emphasize that this is not a proof that breaking discrete log is hard. So if we were able to assume that discrete log is hard, then we could prove that Diffie-Hellman is secure if we could show that breaking Diffie-Hellman implies that one can also solve the discrete log problem. No one's been able to prove that. Instead, the security of Diffie-Hellman relies on a stronger assumption, what's known as the decisional Diffie-Hellman assumption. This is a little bit circular, that we're basing the security argument for Diffie-Hellman on an assumption that was invented because this is what Diffie-Hellman relies on. That seems a bit circular, and indeed it is. But it's a useful way of crystallizing what we really rely on to know that the Diffie-Hellman protocol is secure. And what we're relying on is this property, that g to the xy mod q, and this is how we're computing the key when the xy values, one is the secret value and one is the value that was sent in the previous message. And the assumption is that this value, which is g to the xy mod q, and that's the value that's computed as the key in the Diffie-Hellman protocol, is indistinguishable from random even to an attacker who knows g to the x, g to the y, and q. These are the messages that would be intercepted. So if this assumption is true, that would be enough to prove that the Diffie-Hellman protocol is secure, and then an attacker who eavesdrops on all the messages can't compute the key. Because what the assumption is stating is that there's no way that they could tell that that value, which is the correct key, is any different from a random number, even when they have access to this information. So this is an assumption, and it's even worse than that. It's known that it's not true for certain values. We can show that it is distinguishable from random. So the security of the Diffie-Hellman protocol would follow from this assumption if we knew this assumption were true. We don't, but people have been trying for a long time to break Diffie-Hellman, and so far it seems to be adequately secure. That is certainly not enough to guarantee that it always will be. Next, we're going to talk about some issues in actually implementing Diffie-Hellman. The first issue is that we need to do fast modular exponentiation. One of the steps in the protocol is to compute the generator to the XA power modulo Q, where XA has to be some large random number. And it has to be large and random because if an attacker can guess XA, well, that would break the security of the protocol. So we need to know that this is possible, that we can do exponentiation more quickly than we can do discrete log. So we're going to explore this with a quiz. So how many multiplications are needed in order to compute 2 raised to the 20th power? The straightforward way to do this would be to multiply 2 times 2 20 times. For the quiz, I want you to answer the minimum number of multiplications needed to compute this. And I should point out that we're starting assuming that we don't know anything. Obviously, if you already know the value of 2 to the 20, you can do it without any multiplications. So the answer is we don't need 20 multiplications to compute 2 to the 20. We only need 5. We're doing that by taking advantage of the property that x to the 2a is equal to the x to the a squared. So that means if we're starting from 2 to the 20 Well, that's equal to 2 to the 10 squared. Now we can break 2 to the 10 down into 2 to the 5 squared. We can break 2 to the 5. It's not divisible by 2, so we need to break it down into 2 times 2 to the 4. And now we can break 2 to the 4 into 2 to the 2 squared. And now we can break 2 to the 2 into 2 times 2. So the number of multiplications we need, well, each square is one multiplication, and all of the other ones. So the number of multiplications we have, there's 1 for the 2 times 2. There's 1 for the squaring that. There's 1 for multiplying that result by 2. There's 1 for squaring that. And there's 1 for squaring that. So we have 5 total multiplications in order to compute 2 to the 20. This property holds in general. This means we can compute a to the n using order of log n multiplications. The important thing to point out here is that this is the value of n, not its size. What this means is that modular exponentiation scales linearly in the size, meaning the number of bits we need to represent the power. This means we can make the power a very large number and still compute a to that power very quickly. Diffie-Hellman takes advantage of this property. So for the programming quiz, your goal is to define a fast modular exponentiation procedure, call it mod_exp, that takes as inputs a, b, and q, and returns the value of a raised to the b power mod q, and its running time should be linear in the size, meaning the number of bits to represent the input b. So to do this, we're taking advantage of the property that a to the 2b is equal to a to the b squared. So let's first define a procedure to do squaring, and then we'll define our modular exponentiation procedure. And the easiest way to do this is to do it recursively. So our base case is when b is 0, anything raised to the 0 power is defined as having the value of 1. If b is not 0, well, then we want to check if it's divisible by 2. If it's divisible by 2, we can do this transformation. Then the result is the square of the modular exponentiation of a to the b divided by 2. If b is not divisible by 2, well, then it's of the form 2n plus 1 for some n. So if we break off the 1, we'll end up with something divisible by 2. So that means we can return the result of multiplying a times the result of modular exponentiation, a raised to the b minus 1 power. Now, this is just fast exponentiation. We haven't yet taken the modulos out. If we didn't care how big numbers got, we could do that all at the end. But we want to do that as we go. We're going to add the mod operator to do these modulo q. And that will give us the result of raising a to the b power modulo q using a number of multiplications that's close to the log of the value of b. The next issue in implementing Diffie-Hellman that I want to talk about is this problem of finding a large prime. The protocol assumes that we can start with this value q, which is the large prime number. It doesn't have to be kept secret, but it should be different. And the reason we want it to be different is if there was only one large prime number and everyone used the same one, then an attacker could do a lot of pre-computation based on that number and have a better chance of breaking a Diffie-Hellman protocol. So both protocols require a way to generate large prime numbers. For Diffie-Hellman, you might think, well, maybe we could have some large computing resource do that. Not every participant needs to do this themselves. For RSA, which we'll talk about the next unit, every participant needs to generate their own prime numbers to be able to generate their own key. So we'll talk now about how to do that. So both of these crypto systems depend on finding large prime numbers. So the first question we should ask is, are there enough prime numbers that we can always find a new one when we need one? The good news is that Euclid proved over 2,500 years ago that there are infinitely many primes. And it's a very elegant and beautiful proof. So let's look at how Euclid proved this. We'll start by assuming there are a limited number of primes. That would mean we could define a set consisting of all of the prime numbers and know that it's a finite set with n primes in it. So the elements would be 2, 3, 5, and so forth, and there would be some highest prime which we don't know the value of. So then we'll compute the product of all those primes and add 1. So let's have a quiz. Is the value that we computed as p a prime number? So the possible answers are no, it's definitely not prime. Maybe, we don't know enough to determine that, or yes, it's definitely prime. The answer is, given the assumptions here, p must not be prime. And the reason for that is p is greater than pn, and we said this set includes all prime numbers. That's the assumption that we started with for this proof. And this number is the product of many numbers. All of these are positive, adding 1 to it. So the value of p must be greater than p sub n, and that means, according to our assumption about the limited set of all primes, p must not be prime. So since p is not a prime, that means it must be composite, which means it must be the product of some prime number and some other integer. So that means we can write p as some prime, and we've said all the primes are in this set, so it's something selected from that set, multiplied by some other number. We don't know what q is, other than it must be an integer. So now we have p, which we computed as the product of all these primes, plus 1, which is equal to some prime from that set, times q. So now that we have this, what should we do to get a contradiction and prove that there's no maximum prime number? So the possibilities are to divide by q, to divide by pi, or try proof by intimidation. This is a especially effective proof technique when we're proving something that Euclid already proved. The answer is we don't need to resort to proof by intimidation in this case. We can prove this by dividing by pi. So what happens when we divide by pi? Well, the left side, we have this product of primes, so we're going to still have this product of primes now removing pi from the product, plus the 1, which is now divided by pi, and we divided pi out of pi times q, so we have q here. This is our contradiction. Q is an integer, this is an integer, pi cannot be 1 because it's a prime, it must be some integer 2 or greater, so that means that this is not a whole number. So there's no way we could get an integer as q by adding something that's not an integer to an integer. Thus, we've shown that there are infinitely many primes by contradicting our assumption that there was a limited set of primes. This isn't quite enough to be happy that we can generate large prime numbers when we need them. We need to know how dense the primes are and how to find a large prime. It turns out that the density of primes is such that the number of primes below some number x is proportional to x divided by the natural log of x. So this is log base e. And I won't attempt to prove this. I'll resort to proof by intimidation. This was conjectured by Gauss and then Legendre and proven later. And that means that the probability, if we pick some random number, the probability that that number is prime is approximately 1 over the natural log of x. So the question is, how many guesses do we expect to need to find a prime number that's around 100 decimal digits long? And in computing this, you should assume that this probability that a random x is prime is equal to 1 over natural log of x, even though this is an approximation. So the answer is we only need about 115 guesses. So that shouldn't take too long as there's a quick way to tell if a number is prime. And to compute that result, we computed the log of 10 to the 100. You could do that in Python by using the math library and computing the log of 10 to the power 100, where the base of the log is math.e. That's the constant for the natural log. And that would give you a result about 230. We'll divide that by 2 to get the expected number of guesses we need. So that suggests a strategy for finding a large prime, which is to keep trying guesses until we find one that's prime. If it's not a prime, then we add 1 and we try again. Because of what we know about the number of primes being finite and the density of primes, we know that after a reasonable number of iterations, this will actually find a prime and return that value. We could do a little better if we assume we start with an odd number, and we'll assert that x is not divisible by 2, since that's very obvious that it would be prime, and increment by 2 here. What's missing is we need some way to do this is prime test. So here's a naive way to define is prime. We're going to go through the numbers from 2 to x minus 1, checking whether x is divisible by each of those. If it's divisible by any of those, that would mean that it is a composite number, and we should return false. If we try them all, and it's not divisible by any of those, well, then it's prime. So the question is, would this work? The possible answers are yes, this will work fine. No, it's too slow because the running time is exponential in the value of x. No, because it's too slow because the running time is exponential in the size of x. And no, because there's a silly bug in my Python code. I hope the correct answer is the third choice, that the running time is exponential in the size of x. We're looping through the values from 2 to x. So if x is n bits, that's going to require 2 to the n iterations. And for each one, we're computing this modulo. So this is not going to work if x is large. And in order to use primes in cryptography, we need to find large primes. So we need a faster prime test. So we need a faster test for primes. And what we're going to use is a probabilistic test. And that means if some number x passes the test, the probability that x is composite is less than some value. And we're going to use probabilities like 2 to the negative 128. This is certainly low enough for most uses in cryptography. One way to think about that is if the key size is 128 bits, we already have that probability that someone would randomly guess that key correctly. So the main basis of probabilistic primality tests is properties of prime numbers. One useful theorem about prime numbers is Fermat's little theorem, which states that if p is prime, if we select some number a between 1 and p, and raise a to the p minus 1 power modulo p, the result must always be 1. So maybe we could try lots of a's, and if this equation always holds that a to the p minus 1 is congruent to 1 mod p, well, that would mean that p is probably prime. So the problem is that there are some composite numbers that are known as Carmichael numbers, where this test also holds for most a values. Indeed, it holds for all of the a values that are relatively prime with p. So unless we try all the a numbers between 1 and p, there's a high probability that this will always hold. If we need to try them all, well, this test isn't fast enough. It's still going to be exponential in the size of p. The good news is there's a faster test, which is known as the Rabin-Miller test. Sometimes it's known as the Miller-Rabin test. It was discovered independently by both Miller and Rabin. The main idea was originally proposed by Gary Miller in 1976. He provided a deterministic test based on the assumption that the Riemann hypothesis was true. Michael Rabin, who won the Turing Award in 1976, probably did some of his more important work after winning the Turing Award, which is quite unusual, proposed this in 1980, and that's the one that we'll talk about. So here's how this works. And I'm not going to cover the mathematics behind it, but just enough to be able to implement the test. So we're going to start with our guess n, which must be odd. Obviously, if it's even, it's not prime. And because it's odd, that means we can write it as a multiple of 2 plus 1. So that means we can break n into 2 to some power t times s plus 1. Next, we're going to choose some random a value in this range from 1 to n minus 1. If n is prime, we know that either a to the s is equal to 1 mod n, or we know that a to the s times 2 to the j is equal to n minus 1 mod n for some j, and the j values are in the range from 0 to t minus 1, which is the power here. And that's a big advantage, that we only need to try a small number of values. If we don't find any value that satisfies this, we know it's composite. So the important property that this test has that's different from the Fermat test is that the probability that a composite number passes is always less than some constant. In this case, it's less than 1/4. There are no bad composite numbers like the Carmichael numbers. If we choose a randomly for any composite number, the probability that the test passes is less than 1/4. So now for a quiz. So if we want the probability that our guess n to be composite is less than 2 to the negative 128, how many times should we run the test, each time picking a different randomly selected a value? The answer is 64. So each trial, the probability is 1/4. So we need 64 trials. Each is independent to have the probability reach 2 to the negative 128. So let's restate our protocol. So Alice starts by generating a large prime, and we've seen how she can use that using the Rabin-Miller primality test. Finding a primitive root, we haven't seen how to compute that, but there are efficient ways to do it. And selecting a random secret in the range 1 to the value of her prime, minus 1. And then she computes the value raising g to that power, mod q, sends that to Bob, and I'm showing in this version of the program, I'm sending both the prime and the primitive root. Those could have been agreed on earlier in public. Nothing secret about them. And then Bob computes his value, selecting his random secret and computing yb. And at the end, they can both compute the same key, raising their respective values to the appropriate powers. So we've assumed so far an eavesdropper, a passive attacker, who can hear all the messages on this channel, but can't disrupt the channel. What happens if we have an active attacker? And an active attacker, well, they can change messages on this channel. Instead of just intercepting and listening to them, eavesdropping on the message, they can intercept and change the messages. So is this protocol secure against an active attacker who can modify messages in transit? And the answer is most definitely not. This protocol depends on the integrity of the messages received. One easy way to see how it could fail, if an active attacker can change the value of ya to 1 and change the value of yb to 1, well then Alice and Bob will still agree on a key, but that key would be 1 raised to their secret power, which is still 1. it would be the key value 1, which would be known to the eavesdropper and make all messages encrypted using that key vulnerable. The attacker could also intercept the protocol here and separately execute the protocol with each party. This would make Alice think that has a secure key with Bob, but it's actually a secure key shared with the attacker in the middle. And it would make Bob think that he has a secure key with Alice, but it's actually a key shared with the attacker in the middle. And that means the attack in the middle could take a message that Alice encrypts with this key that's actually shared with the attacker in the middle, can decrypt that message, can then re-encrypt that message using the key that the attacker shared with Bob, and send the result to Bob. Bob will decrypt it, thinking it's a good message from Alice. So this is a very dangerous attack. So Diffie-Hellman can only be used in places where either the integrity of the channel is guaranteed, or there's a way for Bob to find out Alice's YA value and know that it's really Alice. It could also be useful in a case where there's some trusted directory that has the Y values, and Bob could look up Alice's YA value, know the Q and the G values, and then Bob would know that he's communicating with Alice if he trusts this directory. One way to provide that is using a certificate authority, which we'll talk about in Unit 5. So this brings us to the end of Unit 3. And as long as we have a channel with integrity, we have a solution to our key distribution problem. We can use the Diffie-Hellman protocol, where at the end of the protocol, we've established a shared secret. And once we've established that shared key, we can use it to send messages using our symmetric encryption operations from the previous 2 units. We still haven't solved many of the important problems that Diffie and Hellman identified in this 1976 paper. The one that I highlighted at the beginning was digital signatures. And we can't do digital signatures this way because the key is shared between Alice and Bob. That couldn't be used to sign something since either Alice or Bob would be able to make that signature. To have digital signatures, what we need is asymmetric cryptography. That's the main topic for Unit 4. Hope to see you there.
This question tests how well you understand the Diffie-Hellman key agreement protocol. The first 2 statements are, the security of the scheme depends on it being difficult to solve a to the power x equals b mod n for a, given b and an x. The second statement is, the security of the scheme depends on it being difficult to solve a to the power x equals b mod n for x, given a, b, and n. The last 2 statements are, if the value used for g in the Diffie-Hellman scheme is not a generator or a primitive root, the participants might not agree on the same key. The last statement, if the modulus n is not prime, the Diffie-Hellman scheme would still be correct, meaning 2 participants produce the same key, but it might not be secure. Check all that apply. For this question, the second and the fourth options are true. Taking a look at these, the first one is not true because in the Diffie-Hellman scheme, A is public, and so in no way does the security of the scheme depend upon A. The second one is true. To solve for x is the discrete log problem, which in lecture we discussed to show that this is hard. And so the security of the Diffie-Hellman scheme depends on this being difficult. The third one is an incorrect statement. We can see that this statement is correct regardless of G. And so even if G is not a generator, the 2 participants will produce the same key. And the fourth statement is correct. The security of Diffie-Hellman is related to the difficulty of solving the discrete log problem. And for some non-prime numbers, the discrete log is not hard. But yet it would still be correct. This next assignment deals with primitive roots. Your task will be to implement a function, primitive roots, that takes in a small prime number and outputs a list of all the primitive roots of that number. In the IDE, in addition to primitive roots, we have provided a modular exponentiation function similar to what was used in lecture, and 2 simple test cases to use. Here is my solution. It's a fairly straightforward brute force search. First, I write a function that returns if a number, r, is a primitive root. I loop through all the possible exponents to see if the result has been seen before in our set S. If it has, we return false. If no repeats were found, we return true. Using is primitive root, we then loop through all the possible options, checking if it's a primitive root, and appending it to our list. When we've looped through all the possible options, we return our list. The fast modular exponentiation technique used in lecture suffers from an important security flaw. The time it takes to execute depends on the value of the power, which may be secret. This means an attacker who can measure precisely how long encryption takes can learn something about this key. Assuming a simple model of computation where modulus and multiplication by 1 or 2 is free, which costs essentially nothing, but all other multiplications cost 1 unit of time, which of the following modular exponentiations would take the longest? One way to solve this problem is to add a count to the modular exponentiation routine given in class. But I'd like to discuss another way of counting the number of multiplications. First, I want to observe that when a number is represented in binary, it's easy to tell if it's odd or even. All you have to do is look at the last digit. For example, 10 is 1010, and 11 is 1011. And dividing by 2 is a shift right. For example, 20 to 10 to 5 is a shift and then another shift. In our modular exponentiation routine, if our exponent is even, we divide by 2, and it costs 1 multiplication. And if our exponent is odd, we subtract 1 from it, which will make it even, and then we divide by 2. So if our exponent is odd, it costs 2 multiplications. From this, we can easily see that for every 1 in the exponent, when written in binary, we do 2 multiplications, and for every 0, we only do 1 multiplication. Writing our 4 exponents in binary, where 1023 is, that should hopefully be 10 ones, gives us a cost of 20. 1025 has a cost of 13. 4096 should be 1 followed hopefully by 12 zeros, gives a cost of 14. And 4097 gives a cost of 15. So 1023 is our most expensive operation, and that is our correct answer. In lecture, Dave introduced the Rabin-Miller test for primality. For this assignment, I want you to implement this test. The Rabin-Miller function you're going to write will take in a number that may be composite or prime, and target, which defines the desired probability level. The default value, 128, corresponds to a probability of 1 over 2 to the 128. Two useful routines are the modular exponentiation function that we've been using throughout this unit, and randrange, which is a function in the Python library that returns a random integer in between start and end. I haven't provided any tests, but you should be able to find some prime and composite numbers to test with on your own. There is some randomness, so there's a small chance the test will return true for a composite number. But if your target is set high enough, and 128 should be pretty high, it's very unlikely that this will happen. Here's my solution. First, you need to calculate t and s such that n equals 2 to the power t times s plus 1. I've written a helper function, calculate t, which factors out 2's to calculate the appropriate value of t. And then to calculate s, we divide. N tests is the number of tests needed to get the desired probability. Then in this loop, I randomly pick an a between 1 and n and see if I've tried it before. And if I haven't, I break out of the loop and add it to the set of things that I've tried. And then we run our first test, which is to raise a to the power of s mod n and see if that's equal to 1. If that's true, we found an a and we can continue to search. If it fails the first test, we try the second test, which is raising a to the power of 2 to the power of j times s for all j's between 0 and t. If it passes both tests for all randomly chosen values of a, we return true. In this problem, you will be given intercepted messages from a Diffie-Hellman exchange between two people, including p, a large prime number, g, a generator, g of a mod p, where a is Alice's private key, g of b mod p, where b is Bob's private key, a message which has been encoded with g of a times b mod p as the key. You will also be given timing information from the modular exponentiation as described in a previous question. Your job will be to use the side channel to determine the key and decode the message.
Welcome to Office Hours for this week, and I'm here with Adam Sherwin. Job is sick today, so Adam has kindly stepped in. Adam is one of our new TAs who's going to be TAing a statistics course that will be starting fairly soon. So thanks, Adam. What questions do we have for today?
So Astridson asked about the math used in Unit 3. Specifically, what is Z sub q?
So this is a good question, and I have been fairly informal with the math that we use in this class, that I want to focus on the fun parts of crypto, but really to understand things, it's important to understand the math deeply. And so I will put a link to, there's some great free notes from an MIT course that goes into a lot of detail on the math that will have a good definition of this. On the specific question of what Z sub q is, this means the group of integers over multiplication. So if q is a prime number, that is all the numbers less than from 1 up to that prime number minus 1. And a group is defined by the set of elements and the operations. So we use the numerals that we understand to show the members of the group, but they could be any symbol. What matters is what the operations do on those elements. And the multiplicative groups on the integers have the properties that correspond to what we think about integer multiplication having, except for modulo the size of the group. And when it's a prime, these are very useful for cryptography. So that's what I mean by z sub q. It's the multiplicative group of integers, so it's the numbers from 1 up to q minus 1. And when q is prime, that's the same thing as z star q, which is what you'll sometimes see written.
Fernando has a question about the DH key distribution. He thinks the sets A and B should have primes less than P. Is that true?
Yeah, so in Diffie-Hellman, we have the exponents A and B that are picked. They don't have to be related to P other than if P is very small, there's no point picking really large values for A and B. If P is really big, it's silly to pick small values of A. So the exponents are usually recommended to be at least 256 bits, and that's because there's an attack where the work is related to the square root of the size of the exponent rather than to the actual exponent. So if you want 128 bits of security, you need a 256-bit value. You need to select A as a random value up to 256 bits. And that means if P is too small, well, your attacker will go after P instead of focusing on the attack on A. But there's no particular relationship between the size of A and the size of P.
He also has another question about Diffie-Hellman. He wonders why, in practice, it's less accepted than RSA.
So this is a good question, and they're both actually widely used in practice. RSA is more widely used and more talked about. They do different things. So it's not a question of one being thought of as being more secure than the other. And the security of both depends on quite similar problems. Diffie-Hellman depending on the discrete log problem, RSA depending on factoring. There's no reason to believe one of those is easier or harder than the other. And the property that Diffie-Hellman gives you is just this key agreement property. RSA can do more things like digital signatures and encrypting messages. So that's a more versatile cipher. You can do more things with RSA. All you can do with Diffie-Hellman is agree on a key. But there are ciphers built on top of the same ideas as Diffie-Hellman that can provide the same properties as RSA.
Megan Stewart has a question about security in the real world. She saw an ebook company that encrypts the ebook with using as a key the person's credit card number to place reliance presumably on the user to decide whether it's safe to share it.
So this sounds like a really bad idea to me, to be embedding personal information in the ebooks. The goal here is to watermark, to have the digital content specific to each user in a way that if they distribute copies of it, they put it on a file sharing site or they abuse the copyright in some way, that it can be traced back to them. And there's been quite a bit of work on using cryptography to make watermarks, especially in videos, but also possibly in books and images. You can embed something that makes each image unique and is hard to remove without breaking the image. This is probably much harder to do for plain text than it is for video, just because you can't really modify the text, but you could do things that, and this gets a little towards steganography, where you're hiding a message inside something that looks like an unencrypted document. So you could be doing things where you're varying the spacing, or you're changing things that don't really affect the content, or in the embedded information in the ebook that you don't actually see when you read it, you could be hiding some extra information which could embed the identity of the person who bought the book. That would be possibly easy to strip out, so that's something that you need to worry about if you want to use a watermark. In this case, it seems like it's really improper way to treat the customers if they're not knowing this is happening, and it's especially if it's their credit card information that could be used in a way that's abusing the user. But there are legitimate reasons to want to do watermarking of digital content like this, and cryptography provides a great way to do it. And the challenge if you're doing it for something like video is you can do a lot of things to modify the video that might get rid of the watermark. So simple things like using the lowest bits in each pixel to encode the watermark, well, those are really easy to remove because you can change all the lowest bits in the pixels without changing what the video looks like. So there are lots of clever schemes that try to do things that are hard to remove, like changing the timing of black screens between scenes and doing things that are more pervasive in the whole image but still don't make the content broken. So there are lots of social issues here about whether you can secretly track people and whether that should be illegal or encouraged, or what kind of authorization you need to do that. And then there are interesting crypto issues of if it seems acceptable to do this in some contexts, like when a Hollywood studio is distributing a movie in previews, they have a pretty good reason and good understanding with the people they distribute to that they want to keep close track on it and find out if anyone's leaking copies early, to put a watermark in those things, to find a way to do that cryptographically that can't be easily removed and doesn't damage the content in ways that are noticeable.
Vipal Dianshu asks about the challenge problems. He wants to know if you can give more explanation on tips and techniques and tricks to help students solve them before the final, to help them prepare.
So this is a tough question, and there's no magic way that I can give you that's going to really solve this. That the way to learn to solve challenges like this is really to practice and to solve increasingly difficult ones. Doing cryptography depends on persistence in a lot of cases. It also depends on creativity and being open-minded. And often people think a challenge is going to be really hard, so they don't try the easy things. So definitely to make sure that you understand what the challenge is asking for and think about the easy things first before assuming that you have to try something really complicated. And it's also a big difficulty is deciding, are you on the right path and should you keep trying that, or are you stuck in a rut and you need to try something different? And this is one of the things that makes cryptography hard. The challenge in this class are all contrived challenges, that they are intended to give you a sense of what it would be like to break a crypto system that's not contrived to be breakable. But that's a little different, and that means there's it's a challenge for us to construct ones that are good. I know there was a lot of grumbling about the challenge in homework 2, that many people spent a lot of effort on it trying to do complicated things to break it and learning about random number generation and the different ways to do that. And I hope you found that worthwhile and got something out of it. It turned out the actual sequence was quite easy to break if you looked at it in the right way. It was not intended to be quite as easy as it was, and I apologize for some of the obvious breaks in it, obvious flaws in it. I won't say specifically what they are now because I know some people still want to try the challenge on their own. But that was a mistake on my part, and I'm sorry that it turned out to be as trivial once you looked at it in the right way as it was. But it was intended to be something where you could break it without doing a lot of research into other types of random number generation schemes. That wasn't the intent of the question. The intent was, if you looked at it different ways, looking at the bit patterns, looking for any kind of patterns in the sequence, that would be what you need to break it. And we will have some interesting challenge questions for homework 4 that will scale up the levels of difficulty. So I think one of the things to get better at solving challenges is to have the practice of solving ones. You build your confidence as you solve easier challenges and move on to harder ones. So what the challenge for homework 4 will be, there'll be some that we give you some pretty good hints about how to solve, and we think will still be hard and involve an interesting challenge to solve them. And there are others that we're not going to tell you about what to solve, and we're not going to tell you which ones are the easy ones and which ones are the hard ones. So this is going to give you a different kind of experience solving a challenge. I hope people enjoy it and get something out of it. Definitely to be able to attack it, the first step is to understand the underlying crypto behind it. And that hopefully will come out of the lecture in solving the other problems. But the short answer, and I'm getting a little bit rambling because I don't have a good answer that says if you do X, Y, and Z, all of a sudden challenge problems will get easy and you'll be able to break all these known crypto systems. That it really takes practice. It also takes sort of having an open mind and thinking about different things to try and creativity. But the way to learn is to practice and to try to solve increasingly hard challenge problems. The other thing that is really the way to learn is to work with other people. If you can do that with someone in person who's experienced at solving the kinds of problems, that's really the best way to have that kind of back and forth. If you can do that on the forums, that also is great. And so the challenge problems that have worked well, we've seen a discussion in the forum where people have suggested the different approach they've tried. Other people might add to those or suggest an alternative. Those are the things that will really help you develop in terms of solving problems like this, having that kind of discussion and learning about approaches other people take, but still putting the work in to try to think of ways to solve it yourself. So I hope you'll enjoy the future challenge problems, and they will give you a good sense and build your confidence at solving them. I realize that it can be frustrating, and that's part of the difficulty is if you knew you were on the right path and making progress every step, well, that would be great. but that's not usually the way things work in cryptography.